I don't know. Probably he's the guy to ask. I think so. Is that that Gopi goes by Gopi, right?
Yeah.
But, or you'd also know how to correctly pronounce.
Somebody told me actually his name is just the people that made it. I haven't got off at this.
Oh, I think you should actually prefer it. Oh dear.
But I've been calling him Gopi all these years.
Okay, sure. In any case, he's not here, so.
Why not?
The point is, he is, but his wife either just gave birth or will give birth.
He's seeing none of the worst with the jet lag. Oh, no jet lag. Thursday. I was here.
Nice to meet you.
This direction was easy. I guess you never
Sorry. I came at 7 a.m. morning, but I got that much.
At a certain age.
Yeah, tomorrow. Yeah.
Still dark outside.
No, so we need that tomorrow.
Okay. Hi, everyone. In. Hi, everyone. Welcome to the Simons Institute. I'm Shakti Goldas. I'm the director of the Simons Institute. We are a collaborative research institute, and we are dedicated to regulatory science and joint fields. We typically run 2 programs each semester, each attracting around 70 visitors, junior visitors, senior visitors to Berkeley, and each including a boot camp. This is boot camp and several workshops that bring even more visitors here during the week. This semester, one of the programs is Air Curtain Codes Theory and Practice, and this is the boot camp for this program. So welcome to the program. And I first of all want to thank the organizers for organizing the program. And an excellent set of speakers for this week already. Mary, Venkat, Jill, and Gopi, and Henry Fitzer. I think everybody here is except for Gopi, is that correct? So raise your hands. 1, 2, no Henry's there. 3. So I'll hand it over to Venkat in a minute, and he'll introduce the boot camp specifically. But I guess in general, when we have boot camps here, the goal is to sort of an icebreaker for the program, both scientific and social, to get everyone on the same page on what the sort of spectrum of the program themes are and what are the important problems in the state of the art of the field. And then a year from now, there's a reunion usually for each program, which sort of says what has happened in this year, because often what happens during these programs is that you start collaborating, you start to work, but all of it is accomplished within later on. Although I don't want to tell you what actually accomplishing something during the program. We're just saying that if you don't, there is stuff that happens later on. And in a reunion, we usually see a lot more things that would happen during the semester. And you'll also be asked to update a research report or write a research during the reunion. And what else? Just speaking as a director, we're always looking for new programs and new ideas of how to better our collaborations. So I'm welcoming any input from the participants. In terms of logistics, I guess as you saw, we have snacks, we have coffee, we have food during the breaks, but during lunches you're on your own. And we hope you can enjoy what we provide, but not in this room. So in other words, I hope you can enjoy what we provide, but you're not allowed to actually eat and drink in this room. And masks, this is really little COVID, but as you know, there's sort of COVID coming again, so we recommend them, although we don't require them. The lockers available, the Wi-Fi is Cal Visitor or Eduroom, for those who have accounts. At 4:30, we're going to have a reception today where we sort of will try to go to people and introduce yourselves, and we'll introduce the staff, so we highly recommend you to show up. It's like 4:30 to 5:30. Our videographer today is not Aline. Hi. You want to introduce yourself?
I'm Sam.
Sam.
You have a microphone right there?
Oh, for example. So Sam will tell us when we should use the microphone, and if you have any problems with your slides or something, Sam is our man. Finally, a big thanks to our organizers, to Ashley, who's the event coordinator, and everybody else on the team. They work for and really have set up for all the local arrangements for this meeting and this event. And feel free to ask Ashley and her team if you have any questions. I think at this point, I'm going to hand it over to Venkat. Welcome to Simons. Thank you.
Good morning, everyone. My name is Venkat Guruswamy. I'm a senior scientist at Simons Institute and also a co-organizer of this program. And on behalf of all my co-organizers, it's my great pleasure to welcome you all to this program. We are all looking forward to a really fun and productive time advancing frontiers of error correcting codes. As Shafi said, the boot camps are sort of unique in the Simons Institute programming because they kind of really get people up to speed very quickly on research frontiers, and they also have a really long shelf life after this week too. Those videos are some of the most watched by worldwide by graduate students, researchers of all seniority. So no pressure on the speakers, but this is a really valuable resource. And of course, we're trying to focus on some topics where there has been a lot of action. Now, coding theory by itself is a very broad field, bringing together math people, information theorists, computer scientists, and also many different noise models, many different directions. And even focusing on directions where there has been lots of progress in the last 5 years, there is still a big list. So with all that in mind, we have curated a few topics where there are some interesting progress, and also we have a lot of local expertise. So they could, foster collaborations, things like algebraic codes, locality. And given the strong synergy we hope and anticipate with the parallel quantum program, we have 6 hours of quantum error correction in the boot camp. And we also have some other classic topics like probabilistic and combinatorial methods, polar coding, and so on. And this, of course, is by no means exhaustive. And they're already on the Zulip channel, which you should join if you haven't already. There's lots of ideas on reading groups on some other topics, like pseudo-randomness comes to mind and other things. So there's going to be lots of different threads, and this boot camp is an introduction to a few of those. With that said, I'll just remind you about, again, the reception today at 4:30, and I'll hand it over to Mary, who's our first speaker, and also will give a little more details about some logistics.
Thanks so much, Venkat. Hi, everybody. So before I dive into the first technical talk, I have just a few logistical announcements and things. Let's see if I can get this one. Great. So the first thing I want to say is just reiterate thank you to the Simons Institute and its amazing staff for helping make this program possible, both this week's boot camp and also just the whole semester. I'm so excited for the semester. The staff here is incredible. Thank you so much. This is amazing. A few quick announcements. So I think Shafi mentioned that at some point we will be putting together sort of a report of all of the things that happened during this program, it seems like it might be helpful to start putting together that report in real time rather than trying to remember a year later what happened. So with that in mind, we're looking for volunteers to put together a report for this workshop. So let me know if you're interested, if you take good notes or if you want an incentive to take good notes. This is an excellent time to do that. So let me know. You can just ping me in person or by email or on Zulip or whatever. And speaking of Zulip, long-term visitors, please sign up for Zulip if you haven't already. You should have gotten plenty of spam from me in your email about how to sign up. Let me know if you're still having difficulties. Great. And one more quick announcement, speed talks. So you might have noticed if you looked at the bootcamp program that we have 2 chunks of speed talks, one on Thursday and one on Friday. And this is an opportunity for all y'all to tell us what you are excited about. This can be anything like open problems, cool results, fun techniques, or just an introduction like, hi, my name is so-and-so, and here's a quick summary of what I work on. Yeah, so we really hope that this will be an opportunity to get a little bit more beyond the topics that we're talking about in the boot camp, to see, to get a chance to see what everyone's working on and hopefully to form connections and foster collaboration. So please do consider signing up for a boot camp. You can scan this QR code to submit a link. There's like just a Google form, or there's also a link on Zulip and in your email inbox. And I'll be throwing this up again later. Oh, I just realized I'm wearing a lapel mic. I don't need this mic. How do I turn this off? I'll just leave it and then turn this one on. Is this working? Good. All right, sweet. Cool. Okay, so yeah, please submit a speed talk. That'll be great. Okay, and then I just wanted to say one quick note about sort of the goals of the boot camp and the structure of the boot camp. So as Venkat mentioned, he sort of talked a little bit about the topics that we're going to cover, but I want to maybe go just one level higher than that and mention sort of the ultimate goal of the boot camp. So like Venkat and Shafi said, is sort of to get everybody on the same page and really to foster collaboration, because we have so many different communities here. We have folks from CS, math, engineering, physics, all of these things, and we want to be able to work with each other and talk to each other in the upcoming semester. And our strategy for getting everyone on the same page and giving everyone a common language is focused on giving us all sort of some common techniques and problems. So the idea is if I learn about your shiny new hammer, your tool, then I might be like, oh, I have a nail for that, and like maybe we'll work together. Or if I hear about your open problem, your nail, I'll be like, I think I've got a hammer in my toolkit that I could like take a swing at that with, and then maybe we'll work together. So that the hope is that by sort of focusing on techniques and problems, we'll find points where we can sort of leverage all of our diverse strengths. So we've asked the bootcamp speakers to please highlight these as they show up in their talks. I'm going to be doing it with these silly little cartoons. So these will show up repeatedly throughout my talk, and maybe some others as well. Okay, so just keep an eye out for that. And always, it'd be nice to sort of actively have in the back of your head do I have something in my toolkit that would complement what we're seeing on the screen? Cool. Okay, so with that out of the way, let me get started with the actual talk, which is some algorithms for some algebraic codes. Okay, so what is this talk about? Or these 2 talks, actually, this one and then one after the break. So as the title suggests, it's about algebraic codes and some algorithms for them. I was thinking about what to talk about. And okay, there are a lot of algebraic codes, and there are a lot of algorithmic things you might want to do with them. And I'm not going to read all this stuff because the point is it is too much. So I am not going to be able to, unfortunately, talk about all of algebraic codes and all of the algorithms for them. Instead, I'm going to focus a bit more narrowly, but hopefully the trade-off will be that I'll have a coherent talk. So for algebraic codes, I'm going to really just focus on Reed-Solomon codes, sort of the most classic algebraic code, and then a few friends. And algorithms for them, I'm going to be really focusing on just one algorithmic paradigm, which I'll call the interpolate a polynomial and find some roots paradigm. We'll see a few examples of what this is. And of course, I'm necessarily going to omit a lot of cool stuff about algebraic algorithms, or algebraic codes and algorithms for them. If I omit something that you really love, that's a great thing to give a speed talk about. Okay, so what's the plan? So there's 2 talks. In this first talk, I'm going to give 3 examples of this paradigm, just so we sort of all understand what it is. Those 3 examples are the Berlekamp-Welch algorithm, the Guruswamy-Sudan algorithm, and an algorithm due to Guruswamy and Wang. Not clear why I am giving this talk instead of Venkat, but there we go. And then in the second talk, we're going to sort of build on that framework and talk about improvements that one can do on this, including things like leveraging locality, distance amplification, and alphabet reduction. So this first talk, and of course, along the way, we'll highlight several open problems. Yeah, so this first talk is going to have more technical details, slightly more classical results. All of these are sort of at least 10 years old. The goal here of this first talk is really just to get us all on the same page and teach us this paradigm. And the second talk is going to be a little bit more hand-wavy. I'm not going to go into all the technical details, just sort of give you a flavor of the ideas. And this will be more recent results. And in the second talk, I'll really try to emphasize like what is the state of the art and what are some big open problems. Okay, so that's the outline for these two talks. Let's get started with talk one. Oh, and I should say, please do stop me if you have any questions. I suspect I have more material than I can cover, so I'm going to have to stop anyway. So I want to go at a speed that everyone can follow. Great. Okay, so talk one, 3 examples of this basic algorithmic paradigm. But first, terminology. Okay, so I'm just going to sort of quickly set some terminology. I'm assuming that since y'all are here for a program about error-correcting codes, that most people here are familiar with the basics of error-correcting codes. That said, like I said earlier, we're all coming from different communities. We all have different language. So if I am saying something that doesn't make sense, please do slow me down. But I am going to go a little bit fast through this stuff. Okay, so terminology. So for me, a code is just a subset of a space, sigma to the n. So I'll draw it like this. This big blue blob here is sigma to the n. And I'll draw my code as points here. And these points I'm going to call code words. So these are vectors of length n over the alphabet sigma. So we'll call sigma the alphabet. And for this talk, this is a talk about algebraic codes. So my alphabet is always going to be a finite field, fq, or sometimes it'll be a vector space over a finite field, f2 to the s. And again, this is a talk about algebraic codes. So I'm going to be focusing on linear codes in particular, which means that C is going to be an fq subspace of sigma to the n. Okay. So far, this is not a very interesting definition. A code is just a subspace. The thing that makes a code interesting and useful is its combinatorial properties. And sort of the most basic combinatorial property of interest is distance. So the distance of a code is the minimum Hamming distance between any 2 code words. And I'm going to denote it delta of C. So it's the minimum Hamming distance between any 2 distinct code words. And here, I'm always going to use delta to denote Hamming distance, which is just the number of positions on which 2 vectors differ. And I'll use a lowercase delta to denote relative Hamming distance, which is the fraction of coordinates on which 2 vectors differ. Cool. Okay, so why do we care about distance? Well, the reason is that we want our code to be able to do error correction. And so we imagine that we're going to be using these code words to transmit information. So the basic setup here is that the code words are going to be in bijection with a set of messages that live in sigma to the k. And if we want to send some message, let's say this one, what we're going to do is we're going to encode it as a code word. Right, so we fix some map that maps messages to code words. And the hope is that then if something bad happens, we're able to recover. So something bad happens in this picture means that the code word gets perturbed a little bit. So we're going to see throughout this boot camp several different definitions of bad things that can happen. For my talk, something bad is going to refer to adversarial errors. So a bad guy, an adversary, picks some t positions in the code word and gets to munge up those positions, or gets to edit those positions however they like. So in this picture here, that means that this code word is going to be perturbed a little bit. And this tells us why we care about distance, because if t, the number of errors, is less than half the distance, we can see that by the triangle inequality, you can sort of just round back, at least in principle, to that code word. And so the goal will then be step 3 to decode and recover the original message, even though there was a little bit of error. And so this is sort of the main algorithmic task that we're going to be focusing on, is how the heck do we do this decoding algorithm efficiently? Great. And then there's one other thing that I want to define, which is the rate of a code. So the rate of a code, which I'll always denote capital R, is defined as the log of the size of the code base the size of the alphabet divided by n, which is the same as k over n, where k here is the length of these messages. Okay, so you should think about this. This is the message length divided by the code word length, aka like the number of bits you wanted to send or store or whatever, divided by the number of bits that you actually ended up sending or storing, or sorry, maybe not bits, but symbols in sigma. So this is a number that's always between 0 and 1. We want it to be as close to 1 as possible, because that means we have as little redundancy as possible. Okay, so this is all of my terminology about coding theory in one slide. Are there any questions? Everyone's on the same page? Fantastic. Cool. Okay, so one more piece of notation. So I'm going to be talking about algebraic codes. I'm going to be talking about evaluation codes. So just a framework for that. We're going to define an evaluation code. We need to pick a collection of points, which I'll call curly p of size n, as well as a collection of functions, which I'll call curly f, that max the points in curly p to this alphabet sigma. And then these are going to define an evaluation code C, which is basically all the code words that look like this. So you pick a function f in curly f, you evaluate it at all of the points in curly p, and that gives you a vector. You look at all these vectors, that gives you a vector. A classic example of evaluation codes, which is the one we're going to be focusing on in this talk, is Reed-Solomon codes. And so for Reed-Solomon code, the alphabet is just some finite field, fq. Curly p, the set of points, is any set of n distinct points you like in the field. And curly f, the functions are just all of the polynomials over fq of degree strictly less than k. So this is a code with dimension k, or message length k, and block length n. And the code words just look like this. All right, so there are a lot more examples of evaluation codes. So here we said Reed-Solomon codes, which curly p is any set of size n, curly f is polynomials of degree less than k. But you could also imagine, for example, Reed-Muller codes, which is the multivariate version, or algebraic geometry codes, which is some more exciting version that I'll talk very briefly about in the second talk. Or multiplicity codes, where you also include derivative information. I'm going through these very fast and not actually saying what they are, because the point is just that there's a lot of these. But we're going to focus on Reed-Solomon codes because I think the algorithmic ideas are sort of best explained for Reed-Solomon.
Sorry, can I ask you a question?
Yes.
Should I think of there as being one code for each choice of function in curly f, or the code is defined by the entire set of curly f?
Right, yeah, so the question is there a code for each function in curly f, or is the code defined by all of curly f? The code is defined by all of curly f.
Okay, so I'm always evaluating on every polynomial.
Yeah, so formally, here's the definition of this code. Right, so it's a set, right? A code is just a set. And what are the items in the set? They're indexed by the functions f and curly f. And for each function f, you get a different code word. So you can think about f as being like your message, and then a list of evaluations of f as being the encoding of that message. Yeah, great question. More questions at this stage. Great. Cool. Okay, so we're focused on Reed-Solomon codes. Everyone's cool with what Reed-Solomon codes are, so we're just evaluating low-degree polynomials and writing down a list of evaluations and then looking at the set that generates. Right, and so for the rest of talk one, we're going to see 3 examples of an algorithmic paradigm for decoding Reed-Solomon codes, or the last one is going to be folded Reed-Solomon codes, which is kind of a rip on Reed-Solomon codes. And these are all examples of the same paradigm. So I'll give the 3 examples and then say the paradigm generally. So the main point of this first talk is sort of to really hammer home this new technique, or it might not be new for some of you. I know it's not new for some of you, but to remind you perhaps of this new technique, or to put us all on the same page of this technique. So I am going to go through a few more of the details, and yeah, we'll see these sort of 3 nails that we can apply this to. But there will be more open problems, so I'll talk a little bit at the end about open problems, and there'll be a lot more in the second part of the talk. Okay, so let's get started with our first example here, unique decoding of Reed-Solomon codes and the Berlekamp-Welch algorithm. Oh, which I have a title in Berlekamp-Welch. It's an extra K. Great. Okay, so before we talk about what the algorithm is, let's try to formalize what the problem is. So we're trying to do unique decoding for worst case errors. What does that mean? Right. So let's see the Reed-Solomon code, which we've just defined. So the code words are given, so each code word corresponds to a function f, which is a low-degree polynomial. So the first thing I claim is that the distance of this code C is n minus k plus 1, where n is the number of evaluation points, k is the bound on the degree, and plus 1 is plus 1. All right. So why is this the case? Well, let's just look at 2 distinct code words in this code. Right? They're given by 2 different polynomials, f and g, each of degree less than k. And we want to know in how many points do these 2 differ. Okay? well, we can sort of draw a picture, like maybe F looks something like that, and G looks something like that. And then we look at that and say, well, okay, how many places are they the same? Well, at most k-1 places, because two polynomials of degree at most k-1 agree at most k-1 points. So these like cubic-y things that I've drawn agree at most 3 points. And so that means that there's at least n minus k plus 1 points of disagreement, which by the definition of distance means that the distance is n minus k plus 1. Make sense? Cool. And this is optimal. It meets what's known as the singleton bound. So it turns out that Reed-Solomon codes get the optimal trade-off between rate and distance, which is one of the reasons why I like them so much. They're very easy to define, and it's very easy to see that they sort of optimally trade off between these two parameters that we care about. So that's fantastic. Cool. Okay, so now let's think about what we want to do with these codes. So now we know the distance. So we know that the picture, the little cartoon, looks like this. All of the points are separated by at least n minus k plus 1. So that means that if an adversary introduces less than half that number of errors, we should be able to recover it, right? So if the adversary introduces t errors, so on the one hand, that means that what we see is something like this. We see some function g evaluated on these points, alpha 1 through alpha n, so the points in P. And this function g doesn't necessarily have to be a low-degree polynomial, it's just some function, but we're promised that it agrees with f, our target low-degree polynomial, in all but t places. And up here, the picture is like g is pretty close to f. And by the triangle inequality, if we draw like a Hamming ball of radius t around g, that means that there's f is the unique code word that lies in that Hamming ball. So at least in principle, we should be able to recover it, and that is our goal. Given g, recover f. We want to do that efficiently. So this is the problem. Does this make sense? Great. All right. So is there a question? No. Cool. So let's see how to solve the problem. So we'll do this with the Berlekamp-Welch algorithm, which I have spelled correctly this time. So this is a slightly non-standard presentation so that it can lead a little more nicely into the next thing, but it's basically the same algorithm. Okay, so I'll say the algorithm kind of at a high level with lots of holes in it, and then we'll go through the analysis and kind of reverse engineer how to fill the holes. Okay, so here's our algorithm. As input, we're going to take a function g evaluated on these points alpha 1 through alpha n in P. And we're promised that there is some low-degree polynomial, so some polynomial f of degree less than k, so that g is close to f in Hamming distance, closer than half the distance. Okay, and our goal is to recover f. Great. So there's going to be 3 steps to our algorithm. The first step is to interpolate a polynomial q of x, y, so a bivariate polynomial. And this polynomial is going to have a particular form, so it's going to be linear in y and some other degree in x, and we'll have to figure out what that other degree is in a moment. And we're going to interpolate it so that it vanishes on points that look like alpha comma g of alpha for alpha in curly p, where g is our input function. Okay, and also this should be a non-zero polynomial. Obviously, the zero polynomial should do this. I'm going to forget to say non-zero repeatedly. Whenever I say interpolate a polynomial, I mean a non-zero. So that's step 1. Step 2, which is not actually an algorithmic step, but is sort of a step that's useful for the analysis, is to assert that when I plug in f of x for y, I get a polynomial that is identically 0. Okay, so I will do this assertion. That's step 2. And then step 3 is, based on that assertion, I'm going to somehow solve for f. So this is the outline of the algorithm. So there should be several questions at this point, unless you've seen this before. But 3 natural questions are, okay, why can we interpolate this polynomial? Why does such a q exist, and how do we find it efficiently? The second thing, why is this true? Why is it true that when we plug in f for y, we get a polynomial, a univariate polynomial that's identically 0? And then step 3, okay, how do we solve for f? And I'll spoil it a little bit and tell you the answers. And these 3 questions are going to appear for all of our 3 examples, and they're always going to have the same answer. So the answer to question 1 is linear algebra. Right, basically, interpolating a polynomial, right? You're setting up a linear system. Your variables are the coefficients of the polynomial. You have these constraints, which are linear constraints on the coefficients. So we're just going to count the number of coefficients, so count the number of variables, and count the number of constraints. And as long as the number of variables is strictly more than the number of constraints, that means we have a non-trivial solution. and we can find it using our favorite linear algebra techniques. Great. Okay, so that'll be the first question. The second one, why is it true that this univariate polynomial is identically equal to 0? The answer to that one is going to be because low-degree polynomials don't have too many roots. So our strategy here is we're going to show that this univariate polynomial, on the one hand, has a bunch of roots, but on the other hand is relatively low degree. And we'll show that it has more roots than its degree, and that means that it must be identically 0. Right, so that will answer that question. And then step 3, solve for f. How do we do that? By staring. So in this example, it really is by staring. We're looking at like, obviously, you solve for f. This is going to get harder and harder as we see more examples. So staring is kind of a stand-in for look at it and do something creative and pull something out of a hat. But yeah, staring is what I'm going to write down. Okay, great. So this is the outline. Let's go through these steps in more detail now, and we'll sort of see what has to happen. Okay, so step 1, the interpolation step. So we're going to interpolate this bivariate polynomial that is linear in y, and we want it to vanish on all of these points. Okay? And let's say that a0 has degree d0 and a1 has degree d1, and we need to figure out what a0 and a1 are going to be. Okay, so I already described how we're going to do this. We're going to count the number of degrees of freedom in this linear system, and then we're going to count the number of constraints and show that we can get more, we'll figure out what d1 and d0 have to be to make that work. So number of coefficients. All right, so how many coefficients are there that I get to choose for a polynomial of this type? This is not a trick question. It's early in the morning. I want some interaction.
D1 plus 1.
Right, yeah, so I heard d0 plus d1, right, or plus or minus 1, something like that. There's an extra 1 for the constant term. Yeah, so we have d0 plus 1 for a0, d1 plus 1 for d1. Great. Okay, and how many constraints do we have? 1, 2, 3, n. Very good. Okay, this is fun. All right, so we want the number of coefficients to be strictly larger than the number of constraints. So set this thing larger than that thing and solve. And we can say, okay, let's choose d0 to be n minus d1 minus 1. That'll work. Right. So I'm going to replace d0 up there with n minus d1 minus 1. And now actually, now I just have d1, and I don't like doing subscripts in PowerPoint, so I'm just going to turn that into a d. Okay. Okay. So now we have this polynomial, and we know that a1 has degree d that we still need to choose, and a0 has degree n minus d minus 1. Great. And as long as we pick degrees like that, we can do step 1. We can interpolate that polynomial. So now let's move on to step 2. Step 2 is that this bivariate polynomial q somehow explains f in the sense that f is a root of it. Like when you plug in f for y, you get something that's identically 0. Okay, so again, I already explained what the idea is here. Low-degree polynomials don't have too many roots. So let's let R be this univariate polynomial. That is what happens when we plug in f for y. So we get q of x comma f of x. And let's record how many roots there are and what its degree is. Okay, so how many roots does R of x have, at least?
N.
N? Why?
Because the polynomial q of xy vanishes on alpha g alpha. Oh wait, it's fx though. Oh, n minus t.
Yeah, n minus t. Great. Yeah, yeah. So right. So let's sort of back this out. Right. So okay. So the number of roots of R of x is the number of alphas, so that g of alpha is equal to f of alpha, or it's at least that number. Right, because we interpolated q to vanish when we plug in alpha comma g of alpha. So if g of alpha happens to be equal to f of alpha, then when we plug in alpha comma f of alpha, q is also going to vanish. So we get a root every time that g of alpha is equal to f of alpha. And that's a lot, because the whole point was that g was close to f. So this is at least or strictly greater than n minus t points, because they disagreed in strictly less than t points. That was our promise. So we have at least n minus t roots. Fantastic. Okay. And what is the degree of R of x? Oh, all right, it's a little bit gross. I'll just write down what it is, right? It's the maximum of these two terms. Either it's n minus d minus 1, or it's d plus k minus 1, because when we plug in f for y, we're going to plug in a k minus 1 degree polynomial. So it's the maximum of those two things. So we know that R of x is going to be identically equal to 0 as long as the number of roots is larger than its degree. right? So we need n minus t to be at least this maximum, right? And we can figure out what that should be. Or maybe I'll do it on the board here. I won't be doing out very many computations, so let's just do it once, just to. Right. So we want n minus t to be greater than or equal to the max of n minus t minus 1, t plus k minus 1. Okay, so we should probably choose d to like equalize these two terms. So let's n minus d minus 1 is equal to d plus k minus 1. And I should have prepared, because I can't do math at the whiteboard, is d is like n minus k over 2, something like that. Yeah. Okay. And then that means that if we choose d like that, this thing is going to be n plus k over 2 plus minus 1. Like that. All right, I'm going to be a bit fast and loose with the minus ones, plus minus ones, and the floors and the ceilings, and whatever. But OK, so if we say that this is the case, then we solve for this, and we want t to be at most something like n minus k over 2. Maybe with some plus or minus ones, maybe with some floors or ceilings, whatever. Right? But if we do that out, we get, yeah, so t should be at least n minus k over 2 or so. And this is great, yay, because remember n minus k or n minus k plus 1 was the distance, and we want t to be less than half the distance, and that's exactly what we have. So ta-da, fantastic. OK, so step 2 we can do as long as the adversary introduces less than half the distance of errors, which is exactly what we wanted. But there's still one more step. Step 3, we actually need to solve for f. So what do we know? We have this bivariate polynomial q of the form, of this form, so it's linear in y. And we know that q, when we plug in f, is identically equal to 0. So that tells us that a0 plus a1 times f is identically equal to 0. So how do we solve for f?
Minus a0 over a1.
Yeah, exactly. We just solve for f, right? So do polynomial division, and f of x is equal to minus a0 over a1. Yay, we've done it. OK, cool. So here's the algorithm again. I'll just flash it up. Are there questions about what just happened? Yes?
I do have one question. The expression you got for f is really a rational function. How do you know it's really a polynomial? In other words, how do you know that a1 divides a0?
Great. Yeah. So the question is, like, if I just do this, how do I know I actually get a polynomial? Well, it's because I was promised that this f exists, right? And so I know that, like, I know that this thing is true, right? And I know that f is a low-degree polynomial, and so therefore, like, the thing that I get is f. It's a low-degree polynomial. Yeah. Yeah. More questions? Cool. Okay, so how am I on time? 25 minutes? Okay, great. So cool. So we've seen example 1. Oh yeah, question.
Can this algorithm fail? If so, how?
Can this algorithm fail? If so, how? So I just proved to you that it works. So what is it like? It can certainly fail if the hypotheses aren't satisfied, right? So if there is no f that's close. Yes, actually, maybe this goes back to this other question. If there is no f that's close, I can still run this algorithm and I'll get something, but like maybe it'll be a rational function, maybe it will be who knows what, but then I can check that, right? I can look at this polynomial, or I mean, it's not a polynomial, then I'll be like, never mind. And if it is a polynomial, like I can check and make sure it's close or not. Does that answer the question? Great. More questions? Yes.
Can you talk a little bit about complexity analysis of the?
Fantastic. Yeah. So the question was about the complexity analysis, which I just kind of swept under the rug. So as presented, this is polynomial time, right? Or reasonably low polynomial, right? So what do I need to do? I need to do some linear algebra. That's like n cubed at worst. And then asserting doesn't take any time at all. And then solving for f, I need to do polynomial division. So I think the dominating step is the linear algebra. But the reason I'm not talking too much about the complexity is because, so first you can optimize this algorithm and do much better, but there's actually much better algorithm or much faster algorithms for decoding Reed-Solomon codes. I think the Berlekamp-Massey algorithm and riffs on that are actually much faster, and they can be near linear, like n log n, maybe with some log n's. And people have worked really hard on optimizing the heck out of those, and this is not that. So yeah, I'm not. But yeah, it's a good question, and I'll have some references for that later in the talk too. Yeah, question.
How many bits the adversary changes can that figure out into the running time? Like, can you make it sensitive to, like, if the adversary doesn't change n minus k over 2 bits, then?
Great question. Yeah. So the adversary gets to change t bits, which is less than this. But what if the adversary chooses to only change 1? Can you make it faster? So again, the Berlekamp-Massey algorithm, which is not this algorithm, you can, and that's another, like, so if the adversary just changes t bits, then actually you can do syndrome decoding in sublinear time that it depends on t rather than, or if t is sublinear. Yeah, maybe ask me later and we can talk about that. Yeah, can this algorithm, I guess it's stated this algorithm doesn't really get any, I don't see how to make it better if you have less errors. Anybody know?
Could you iteratively interpolate, like change d? Because you can interpolate with lower degree if there's fewer errors, right?
Oh, I see. If you know that t is smaller, yeah, I guess maybe that makes that makes the system you're solving slightly smaller. Yeah, so maybe that just makes it faster. Yeah, that's true. Yeah.
How can anyone come up with this Q?
How can anyone come up with this Q? Do you mean like the form of Q or the?
This is the thing that you're looking for.
Right. That's a great question. Yeah. How do you decide that Q should be linear in Y? So actually, the original presentation of the Berlekamp-Welch algorithm is a bit different than this. So basically, A1 is meant to be a stand-in for the error locator polynomial. So this, you think of this as being a polynomial that vanishes on all of the errors. And then you think of A naught, or maybe negative A naught, as being the received word G, and or G times A1 or something. Yeah, maybe we could talk about it offline, but yeah, this is sort of a retrofitted version to make it lead into the next part of the talk. There is a much more natural way to describe this algorithm, where there's more intuition for what exactly A naught and A1 are. Okay, maybe in the interest of time, because I do have 2 more examples I want to go through, maybe we consider that nail hammered and move on to list decoding. These are all really good questions, but maybe they're pushing a little beyond the scope of the talk. Okay, cool. So, right, so our next example is list decoding of Reed-Solomon codes. This is the Guruswamy-Sudan algorithm. So we all know what Reed-Solomon codes are now. I need to tell you what list decoding is. Okay, so what is list decoding? So like unique decoding, it is a problem that we can solve. So we're going to have our Reed-Solomon code C, and we already know the distance of C is n minus k plus 1, so the picture looks like this. But now, let's say we're in a parameter regime where the adversary introduces too many errors, more than half the distance, right? So down here, what that means is that we're going to get some function g that agrees with f in all but t places, but now that means it might disagree with f in like kind of a lot of places. And geometrically in this picture, that means that g is going to be a little bit further from f. And in particular, if we draw a Hamming ball of radius t around g, f might not be the unique thing in that Hamming ball anymore. There might be more things. So our goal before was to recover f, but as we can see now, at least with worst case errors, this is impossible. There might be multiple f's. We have no way of knowing which one was the right one. So instead, we're going to readjust our ambitions and try to recover a short list of possibilities for f. And there are many different reasons you might want to do this. I'm not going to talk about them right now, although we'll see one application in the second half of the talk. Okay, so this is the list decoding problem. Are there questions about the statement of the problem? Cool. Okay, so here is the Guruswamy-Sudan algorithm for solving this. So actually, for simplicity, I'm not going to present the full Guruswamy-Sudan algorithm, I'm going to present a simpler version known as Sudan's algorithm. So, sorry, Venkat, you're left off. But well, I'll wave my hands at the end for what makes it the Guruswamy-Sudan algorithm. Yeah, so right, so as before, it has kind of the same form because the whole point is that we're doing this same formula again and again. So we'll start with a function g of x evaluated on these points. That's our input. And we have the promise now that the difference between, or that f is close to some low degree polynomial g, but now close is t. And what is t? Well, for now, let's make it TBD. We want it to be as large as possible. Let's go through the algorithm and see what we can get. Okay, so our first step, as before, is we're going to interpolate a polynomial. But now, instead of being linear in y, it's going to be degree dy in y. Otherwise, it's an arbitrary polynomial. And it's still going to vanish on these same points that we had it vanish on before. Step 2 is exactly the same. We will assert that this thing, q of x comma f of x, is identically equal to 0. And step 3 is that we're going to solve for a short list of possible f's. Right? So the things that are different from before are in red. So the thing that's different is that now this is going to have higher degree in y, and we want to return a short list of possible f's instead of all the f's. And as usual, we have these same 3 questions. Why can we interpolate that polynomial? Why is it true that this univariate polynomial is identically equal to 0? And how do we find a short list of possible f's? And my answers are going to be exactly the same. Linear algebra, low-degree polynomials don't have too many roots, and staring. So let's go through these 3 steps and dig a little bit more into these questions. OK, so step 1, interpolation step. We want to interpolate a polynomial of this form that vanishes on these points. OK, and let's say that these polynomials a0, a1 up through a dy have degree dx. So this is just sort of a generic polynomial that has degree dx in d and dy in y. And we need to figure out what dx and dy should be in order to make all the steps work. So let's do the same exercise we did last time. We need to count the number of coefficients, the number of constraints, and we need to choose dx so that the number of coefficients is strictly larger than the number of constraints so that we can find a non-trivial solution to this linear system. OK, how many coefficients are there?
dx plus 1 times dy plus 1.
Great, dx plus 1 times dy plus 1. That's the number of monomials that you get to pick coefficients for. How many constraints are there? 1, 2, 3. And good. All right. We're losing enthusiasm. Come on, guys. I guess it's because there's no coffee allowed in the auditorium. I understand. All right. So how do we choose dx? OK, we want number of coefficients to be strictly larger than number of constraints. So solve for dx. Let's take dx to be n over dy plus 1, and that'll do it. All right, so I'll replace dx up there with n over dy plus 1. And once again, I don't like doing subscripts in PowerPoint, so now we only have 1 dy, so that's going to turn into a d. Great. OK, so now we have this polynomial. It has degree d in y and degree n over d plus 1 in x. And we can move on to the next step. So the next step is we want to say that q somehow explains f in the sense that when we plug in f for y, we get something that's identically equal to 0. So we'll do the same thing as before. So let r of x be this univariate polynomial that happens when we plug in f for y. And let's count roots and compute the degree. So this is exactly the same as before. The number of roots of r of x is the number of alphas, at least the number of alphas, so that g of alpha is equal to f of alpha for exactly the same reason as before. And for exactly the same reason as before, that's at least n minus t. So that bit is exactly the same as the first time. And what's the degree of r of x? OK, we can just sort of, the degree is going to be dominated by this term. We plug in a degree k minus 1 polynomial here. So that's going to give us n over d plus 1 for the AD term and d times k plus 1 for the f of x to the d term. Cool. OK, so now we just want to solve for the d that we need so that the number of roots is larger than the number of degrees, or is larger than the degree, because that will mean that the thing is identically equal to 0. How do we do that? Well, once again, let's choose d to like equalize those 2 terms. I'm not going to do it on the board. I just did it for you. We should, turns out we should choose d. Actually, yeah. So first, let me be fast and loose about the plus minus ones because I am. And so this is like, let's call this n over d plus d times k. And then we want to balance these 2 terms to kind of make this as small as possible. So let's choose d to be the square root of n over k. And we see that this degree is going to be about 2 times root nk. And if we choose things like that, move that up there, then, okay, we want to solve for d so that this is larger than that, or sorry, that we want to see what t needs to be so that this is larger than that. And we see that we need t to be at most n minus 2 times the square root of n times k. Yay? Maybe? Not sure. Okay, sorry, this is a bunch of math. The algebra doesn't matter. But does the outline make sense? Cool. Okay, so we'll come back to whether or not this bound on t is good or not in a moment. But let's finish up the algorithm first by doing step 3, solving for f. So what do we know? We know that we have this bivariate polynomial, q of xy of degree d in y, and we know that when we plug in f for y, we get something identically equal to 0, which means that this is the case. So how many possibilities are there for f, and how could we find them? Any ideas? Yeah, so if we just ignore the x's here, right, this is just a polynomial in f of degree d. So we can, there should be at most d roots of this polynomial, and we can find them efficiently. And it turns out that the fact that these are polynomials rather than just field elements doesn't really matter. The same thing still goes through. So that intuition works out, and it turns out that we can do some algebra and solve for the at most d roots of this polynomial. And remember, d was, we had chosen to be like root n over k, which if k over n is the rate of the code, that's r. So this is root 1 over r. So if you have constant rate code, this is like a constant number of possible solutions. Okay, questions at this point? Okay, so what just happened, we walked through these 3 steps, and we saw that as long as t is less than something, then there's at most a constant number of choices for f, and we can find them efficiently. But is that good? What does this bound on t actually mean? Right, so we said that t has to be at most n minus 2 times the square root of nk. And it turns out you can actually drop that to, this is going from the Sudan algorithm to the Guruswami-Sudan algorithm. And there's basically 2 techniques that one needs to do that. One, we can be a bit more clever about assigning degrees to the AIs. I chose them all to have the same degree. That was pretty wasteful. And the other thing is we can introduce multiplicities. So we can ask Q to vanish with higher multiplicities. So I'm not going to go into it. You can see this paper from Guruswami-Sudan or Berlekamp. Yeah, but so this is the bound that we get. We're still wondering, is that good? So if we factor out an n here, n minus root nk, this looks like n times 1 minus the square root of r, where r is the rate of the code. So turns out that this is something called the Johnson bound, and some combinatorial bound, but I'm going to skip over that for time. And the point is that this does seem pretty good. Like when r is small, this approaches n. And that can be way bigger than half of the distance, which approaches n over 2 as r gets small. So it's like twice as big. That's pretty awesome. But it turns out we could hope to do better. There's something called the list decoding capacity theorem that says that actually the best you could do is not n times 1 minus root r, but instead n times 1 minus r. And r is between 0 and 1, so r is smaller than root r, so this is better. Right? So we could hope to do better. And we want to, and that's what we're going to do in our next example. So before I move on to the next example, are there any quick questions about this example? Yes?
Isn't the baseline always just like evaluating it and then computing the distance metric with respect to all of the potential code words? So like why is there even any bound on t at all?
Oh, I see. So let me see if I got your question right. So you're saying, suppose I don't care about efficiency.
Yeah.
Instead, I could look at all of the code words and see how many, like just pick out all of them that happen to be in this bound.
Yeah, you just accept reject based on within t
Right.
having distance.
Yeah, so you're absolutely right. That is an exponential time algorithm to solve this problem. Maybe I was a bit fast and loose with my definition of list decoding earlier. So when we say that a code is list decodable, what we mean is that actually the number of those code words is sub-exponential, is bounded by something non-trivial. Right, so when t gets too large, it could possibly be that actually there's an exponential number of code words in that ball. And so then we'd have like an output of exponential size, and there's no hope of having an efficient algorithm. But if we know that there's a small number of code words in that ball, then we could hope for having an efficient algorithm. And actually, there's a distinction between combinatorial list decoding, which is, can you just prove that there's a constant number of code words in that ball, and algorithmic list decoding, which is find them efficiently. Actually, for Reed-Solomon codes, this is a big open problem. There are, so open problem. I don't have my little graphic here. We know, advertisement for Jonathan's talk, that combinatorially, some Reed-Solomon codes are list decodable all the way up to this bound. So we know that there aren't too many code words in this ball. We have no idea how to find them efficiently. Yeah, question.
So even if you have like a constant number of code words in that ball, how do you know which one is the correct one? And if you chose like the wrong one, wouldn't that be like a logical error?
Yeah, great question. Yeah, so the question is like, essentially, what is the point of list decoding? I want one answer. You're giving me a constant number of answers. I still want one answer. Yeah, and so I have several answers to that question. So one, we'll see in the second talk actually how you can use this to do unique decoding. But also, it turns out that list decoding is actually just a very useful combinatorial and algorithmic primitive, even beyond coding theory. So it has applications in, for example, complexity theory and algorithm design and things like that. So maybe we can talk more offline about other applications. Yeah.
When we talk about efficient algorithms, it's efficient on what? Like does the number of solutions or like elements that you're list decoding also part of this efficiency or not?
Yeah. So the question is, what's the definition of efficiency, and is the number of these code words part of that definition?
Yeah.
Yeah. So the number of code words has to be part of that definition because I should output all of them, and it takes at least time all of them to output them.
You could tell them that give me the ith one, and then you
okay, that's true. Yeah. Yeah, that I could hope to have some canonical ordering and say, give me the ith one. That's right. Or actually, we'll see. Okay, maybe we won't see given time, but there are algorithms that could produce a description of a subspace that contains all of these things, which would go a little bit faster. Yeah. So right now, I guess what I'm talking about is the time it takes to return all of them, and what I mean by efficient in this talk is polynomial time in n. But you're absolutely right. You could definitely think about other definitions that make sense. Yeah.
The list decoding capacity, sort of that as a bound, is that something where sort of that's as good as we can do? Is that something that comes from the combinatoric point of view or the algorithm? Is it a claim about efficiency or?
Yeah, great question. So yeah, so this list decoding capacity, this is a combinatorial statement. So if you take t a little bit larger than that, then there will be an exponential number of code words in that ball, so there's no efficient algorithm to return them all. Great. Yeah.
10 minutes.
10 minutes? Oh, I thought I had 4, so we'll take 10. Aha, all right, 10 minutes. Well, in that case, I might even be able to do the third example. All right, cool. So let's, maybe we can table further questions. Are there any clarifying questions? These are all really good questions, but I want to get through the last example. People have some sense of what's going on. Cool. All right, so let's consider that nail hammered, and we'll move on to the last one that I wanted to talk about, which is list decoding of folded Reed-Solomon codes. And this is going to get us all the way up to that list decoding capacity thing. So we'll be able to take t larger than n times 1 minus root r. We'll be able to take it all the way up to t times 1 minus r. But first, I need to define what folded Reed-Solomon codes are, because they're a slight tweak on Reed-Solomon codes. Okay, so to get folded Reed-Solomon codes, these are introduced by Guruswamy and Rudra. Basically, you start with the Reed-Solomon code, and I'm picking the evaluation points not to be an arbitrary alpha 1 through alpha n. I'm now picking them to be gamma, gamma squared, gamma cubed, gamma to the fourth, dot, 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 up to gamma to the n, where gamma is a generator of the multiplicative group of the field. So as you power up gamma, you're going to go through all of the elements of the field, just in order. And then what I'm going to do is I'm going to take this code word, and I am going to sort of literally fold it like this. So I'll take the first S symbols and just write them down like that, and the second S symbols, write them down like that, and so on. And what I've done by doing this is I haven't really changed the information that I'm presenting, but I've changed how it's packaged. So I'm going to view this original Reed-Solomon code word as a code word in a code with alphabet F of length n. And after I fold it, I'm going to view this as a code word in a code over alphabet F to the S of length n over s. So I've made the alphabet size bigger. And you might ask, what does that get me? Like, why should that help at all? And intuitively, this is kind of restricting what the adversary can do. Before, let's say the adversary was allowed to corrupt a tau fraction of the symbols, they could choose that tau fraction however they wanted, distributed among any of the symbols. Now they're kind of constrained that, like, if they want to corrupt this one, well, they may as well corrupt all of these others, but they can't correct it, like any old tau fraction of the original symbols anymore. So this kind of constrains the adversary. So this does make our problem a little bit easier. Great. And this is going to give us the folded Reed-Solomon code of length n over s. It's made up of all the sort of folded versions of the code words of the class. Is the definition clear? Yeah. Okay, so let's see if I can. I'm going to have to speed a little bit through this algorithm, so I will wave my hands about some of the details, but I'll try to get through the parts that matter that we'll build on for the next talk. Okay, so here's the algorithm. This is due to Guruswamy and Wang in 2013. It looks a lot like the algorithms we've already seen. No surprise, that's the point. So as input, we have our function g evaluated on p, and we're promised that g is t close to some low-degree polynomial f. But now distance is measured in this kind of like folded Hamming distance way. So on these mega symbols, it agrees on all but t symbols. And t is going to be what we want it to be, is going to be about the block length, which is n over s, times 1 minus r. And that's as large as it can be according to the list decoding capacity theorem that I mentioned earlier. So that's the punchline. Cool stuff. All right. So what are we going to do? We're going to interpolate a polynomial. But now it's not going to be bivariate anymore. It's going to be r plus 1 variate for some parameter r that we need to choose. And it's going to have variables y1 through yr. And the form of our polynomial is it's going to be linear in the y's and have some degree in the x's that we'll need to choose. Second step is exactly the same. Oh, whoops, no. Second step ought not be the same. That type error. We're going to assert that q of x, comma, f of x, comma, f of gamma x, comma, f of gamma squared x, comma, dot, 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 comma, f of gamma to the r minus 1 x. So when you plug in f and then f of gamma x and so on, and for the various y's, we're going to assert that that is identically 0. Sorry for the typo. And then we're going to solve for a short list of possible f's. And we have our same 3 questions as usual. Why do we interpolate that? How can we interpolate that polynomial? Why is it true that this thing identically is 0? And how do we solve for a short list of possible f's? And same answers as before. Linear algebra, low-degree polynomials don't have too many roots, and staring. So in the 5-ish minutes that I have left, let's walk through these steps real quick. Okay, so first step, interpolation step. I'm going to skip this because this is exactly what you expect. We just count the number of coefficients. We count the number of constraints. I actually need to say what the constraints are. You know what, for the purpose of time, we're gonna, so I wrote down what this should do. So this should vanish on alpha, comma, g of alpha, comma, g of gamma alpha, dot, dot, all the way up to g of gamma, the r minus 1 alpha, for some set of alphas. Basically, the idea is we're gonna want this to vanish sort of on these r points, and then we're gonna slide the window down and ask it to vanish on those ones, and slide it down again, ask it to vanish on those ones, and so on. And this is going to give us a whole bunch of constraints. But I think in the interest of time, you can ask me later or read the paper for the details. But we can do out a bunch of math. And no, that was step 2, sorry. It turns out that if we choose D to be roughly like that, then you can interpolate this polynomial. And I know that I'm not fully explaining exactly what are the constraints, but you can ask me later. It's not that important. Okay, and then step 2, assert that, sorry, again, this is typo, q of x, comma, f of x, comma, f of gamma x, comma, dot, 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 comma, f of gamma to the r minus 1 of x is identically equal to 0. Once again, this is exactly the same calculation. We count the number of points of agreement, we count the degree, and we show that the number of roots is strictly larger than the degree. So I'm just going to flash through this because I don't think doing out the arithmetic is very enlightening. But okay, we get, turns out, something like this, that t is at most n over s times 1 minus some stuff. And remember, what we wanted was t over s times 1 minus r. And so if we stare at this and we're like, well, let's take r to be real big, like a big constant. Let's take s to be like a bigger constant. Then this is pretty close to n over s times 1 minus r. And so that tells us how we're going to choose these parameters r and s. So s, remember, that was like our folding parameter. That's how big the alphabet needs to be. And r was, doesn't really matter, some parameter in the algorithm that I just skipped by. But the point is we can make this approximately right. Yay. Okay. And here's the step that I actually want to dwell a little bit on, which is solving for f. Right, so what do we have so far? We have this polynomial of this particular form. And we know that when we plug in, oh, sorry, so many typos, this should be an r minus 1. When we plug in these f's, we get something that's identically 0. And so what does that mean? That means that this thing is identically 0. And we somehow want to pull f out of this. Right? And this requires, I think, a little more creative staring than the previous ones. How do we do it? So I only have 2 minutes. I'm not going to explain how to do it in a lot of detail, but basically the idea is this. Let's ask ourselves, what is the constant coefficient of this polynomial? So on the one hand, it's 0, because the polynomial is identically equal to 0. On the other hand, okay, the constant coefficient of each of these terms is given by f naught times the constant coefficient of ai. So this gives us some linear equation for the f naught, the constant coefficient of f, in terms of the coefficients of f ai's, which we have already interpolated. So we could hope to solve for f naught. So now imagine we've done that. Imagine we know what f naught is. Now let's ask ourselves, what is the coefficient on x in this polynomial, the linear coefficient? Well, on the one hand, it's 0, because the polynomial is identically equal to 0. But on the other hand, well, okay, well, at least in each of these sums, this is, what's the coefficient on x? Well, it's the coefficient on x on this guy times the constant coefficient there. We already know what the constant coefficient there is, so great. Plus the constant coefficient on this guy times the linear coefficient there. Okay, well, we already knew the constant coefficient of f. The only thing that's unknown is the linear coefficient. We now have a linear equation for that coefficient. Let's solve for it. And you can go on in this way, and you end up getting this triangular system of linear equations. And you'll solve for f1, and then use that to solve for f naught, use that to solve for f1, use that to solve for f2, and so on. Right? And then we can solve for f. Hooray! In 1 minute, what am I being fast and loose about? I just told you how to solve uniquely for f. Yeah, Nick.
Why are there only a small number of f's that you
Yeah, that's right. Like,
or there should be a unique solution in some sense.
Yeah, like the thing I just described should return a unique solution. We know that that's too good to be true. So like obviously this linear system isn't going to be full rank. Like I can't actually just solve for f naught. It might involve dividing by 0. I can't actually solve for f1. It might involve dividing by 0. But actually, by like writing out this big linear system and staring at it, you can sort of see that, oh, actually, the number of times that I have to, like the number of degrees of freedom here is actually bounded. I'm not going to, I have it on the slide, but it's a big mess of math, so I'm not going to do that. But the key here that I want to emphasize is that what you can do by staring and then doing some linear algebra is you actually get a description of a low-dimensional subspace. In this case, it's going to be r-dimensional, where r is this parameter that's less than s that we chose. So some constant dimensional subspace that contains the list. So you're going to try to solve this system. There'll be some degrees of freedom, and that's fine. That gives you a linear subspace that contains the list. And that's sort of the thing I wanted to emphasize. Okay, so let me wrap up because Venkat's looking at me. So what have we learned? Yeah, so we've seen this basic paradigm. So yeah, I hope I've like really tried to hammer home this technique. Well, no pun intended, yeah. All right. So we've seen this basic paradigm where we are given as input some function g evaluated at our points. We know it's pretty close to f. We want to interpolate a and like we have these 3 steps. Interpolate a polynomial to vanish on some nice places. Assert that when we plug in f in some way, we get something that's identically 0, and then solve for f, or possibly a short list of possible f's. We had these 3 questions, and we always had the same 3 answers. Great. I want to mention a few open directions, actually, some of which y'all already mentioned. Like, how do we guess the form of this Q? It seems to require a lot of divine inspiration. Like, maybe there's some other cues that we could guess that could be better. And I guess I also meant maybe also the second one, I mentioned just the third one. Can we do something other than low degree polynomials don't have too many roots for step 2? Right? Most polynomials, like if you take a random polynomial over FQ, an expectation it has one root, no matter what its degree is. So like maybe if we gave ourselves a little more freedom and like randomized how we picked it, maybe we could do that step a little bit better. I don't know. I haven't been able to get that off the ground, but yeah, we could imagine tweaking various different aspects of this paradigm. Right, there are open questions about the actual punchlines, but I think all y'all have already highlighted those. So maybe I will skip that. Yeah, go to Jonathan's talk to one about open questions regarding Reed-Solomon codes. And someone else asked about faster decoding algorithms. Yes, that is an open question, although for unique decoding of Reed-Solomon codes has been very well studied. Okay, so I'm out of time, so I will stop, and you can ask me. Probably we don't have time for questions.
Yeah, probably.
Yeah, so ask me during the break if you have questions. In the meantime, sign up to give speed talks, and I'll see you after the break.
Maybe meet 5 after, just to give people